Hey, so as part of my work with the IQC, I've been looking at this algorithm called Krylov in the past few days, and it's an approximation technique to approximate matrix exponentials. And I was really struck by how profound, at least it seems to me, but I haven't heard it anywhere in the quantum community. So I really want to understand if I'm missing something. Is there something I'm missing with this technique? Is it not really as good as it purports it to be? So this video is kind of just to explain the bare bones how the algorithm works, so that hopefully someone comes and corrects me. But at least to me, it seems that a really great technique to approximate sparse Hamiltonians, the evolution of sparse Hamiltonians, and of course that's essential for a lot of quantum mechanics. So I've condensed some of these points into this Notion doc, and let's get started. So the objective is to compute WFT, where WFT is the exponential of AT multiplied by some vector. So the key to Krylov's algorithm here is it's not just approximating e to the AT, but it takes advantage of e to the AT applied on the operand vector to then arrive at an approximation of the whole quantity W of t. So our objective is to find W of t, and we know that by definition W of t, the matrix exponential, is actually the Taylor expansion um, of the is actually the Taylor expansion. And to approximate the series, it's important to note that if you take the truncation of a certain series, these coefficients that you see here, which is like t over 1 factorial or t squared over 2 factorial, these factorials, they're not necessarily the best approximation for the truncated Taylor polynomial. So you could imagine that we truncate it at some point, we take these terms and we change up the coefficients, the numerical coefficients, and you can actually obtain a better approximation of W of t. So as such, we reformulate this our objective to approximate W of t as finding the optimal element within this Krylov subspace of dimension m. So what does this mean? So the Krylov subspace of dimension m is the truncated Taylor polynomial truncated to m terms, but the coefficients are unbound. So it's a set of vectors of each v and multiplied by ta raised to some degree. So this Krylov subspace, you could imagine, is actually a general description of all approximations of the truncated polynomial of the matrix exponential. And that's so we can say that finding the optimal W of t for a given number of terms m is actually akin to finding the optimal element within this set within the Krylov subspace. Okay, so we can further simplify this problem, but I just want to go back and quickly uh, recap what they talk about here. So they say that all polynomial approximations of degree at most m minus one, including this, are therefore are elements of the Krylov subspace of dimension m, as what I said before. And so the first step to go about this Krylov algorithm is to actually generate a set of orthonormal basis vectors to span this set of vectors for this span. And you do that through the Arnoldi procedure, which I need not really go into, but the gist of it is that the Arnoldi procedure outputs two matrices. One is V sub m plus 1, and this basically contains on the horizontal, each column is an orthonormal basis vector for this subspace. And the second is h bar. I don't quite intuitively understand h bar yet, but from what they say, h sub m is a Hessenberg matrix, meaning that it's triangular with an extra subdiagonal, and it represents the projector of operator A onto the Krylov subspace with respect to the basis, with respect to the orthonormal basis that we just generated for the Krylov subspace truncated at M. Okay, so with that in mind, with H in mind, and we know that V sub M is our orthonormal basis set, we can simplify this formulation. And this is what I really found interesting, the way the way they really go about this approximation. So you can say that the optimal Krylov approximation of W of tau, which is equivalent to the exponential of a tau v, can be described completely by the V sub m matrix, since it's a complete orthonormal basis for the Krylov subspace of dimension m. So then by definition, we have that the closest distance from our optimal approximation to the actual W of t that we're trying to approximate is going to equal to the minimum distance between the best element of the Krylov subspace and what we're trying to approximate. And that best element is actually the optimal set of y coefficients applied on the set of orthonormal basis vectors. So it's like the optimal linear combination of the orthonormal basis vectors, which kind of makes sense because the orthonormal basis vectors are completely span the Krylov subspace. So it's basically just saying the optimal vector in the Krylov subspace is what we're looking for here. But why it's phrased in such maybe it seems like a peculiar way is because, well, this is actually a least squares problem, and it turns out that the solution to least squares problems are well known, and the best set of coefficients, again, that's what we're trying to find here, to these coefficients to approximate best W of tau, can be stated in terms of the Moore-Penrose inverse of V sub m, which is this. And you don't need to know what the Moore-Penrose inverse is. All you need to know is that it expands actually into this. That's what it is by definition. And recall that V sub m transpose times V sub m is actually the identity matrix, because V sub m is a matrix full of orthonormal basis vectors. So if you take the transpose of it, and you multiply them together, you take the matrix product, you're only going to get one along the diagonals, because each basis vector is orthonormal to each and every other basis vector in the matrix. So that gets canceled out because the inverse of the identity is the identity, and you end up with V sub m transpose times exponential of tau a times v, and this will give you your optimal set of coefficients to apply your optimal set of coefficients for the Krylov subspace. And if you remember, V is actually beta times V sub m times the unit basis vector of 1. Beta is just a norm of V, and that makes sense because V sub m just extracts the first unit basis vector of V sub m is actually V, or is actually in the direction of V. So once you extract that and multiply by the norm of V, you'll get V. So we can sub that in for W opt, and W opt again is V sub m times this quantity here, and we have V sub m here, and this quantity here is derived from, is substituted from here, and instead of V, we substitute what V actually is. And that ends up equaling, you just shuffle around the terms, and you basically get this term in the middle here, which is the core part of the Krylov logarithm. So this is where the core approximation comes in, because this is the optimal approximation to find the best element, again, in the Krylov subspace. That's what we're looking for. But it's still awkward since we need to compute exponential of tau a, right? So like, what's the point of even what's the point of all this if you still have to compute the exponential just as you would have had to before? So here's where the key approximation for Krylov logarithm comes in that I found really interesting. So they say that V sub m transpose times exponential of tau a times V sub m is approximately equal to the exponential of tau times V sub m transpose times a times V sub m. And this is a very big deal, since the latter is an exponential of a matrix of dimension m, which is usually far less than the dimension of the matrix A, n. And the author actually says that usually, if you're dealing with sparse matrices A, n can actually range on the order of thousands, and m is capped at 30. So this is a drastic difference in the computational time it takes to evaluate these two matrix exponentials. And I don't fully understand this intuition, but they say that this approximation makes sense because, in a sense, the projection of the exponential operator with respect to the v sub m basis, which is an orthonormal basis for the Krylov subspace, is approximately the same as the exponential of the projection of the operator with respect to the same basis. So essentially, so essentially the projection of the full exponential operator, which we have here, converted into the orthonormal basis that we have, is approximately equivalent to if you just take the exponential of the operator already converted into the v sub m basis that we were talking about. So then using a previous result from our Arnoldi algorithm output, we know that this other matrix that the Arnoldi algorithm outputs, kind of like a Gram-Schmidt alternative, but for this scenario, is that this H sub m matrix, this Hessenberg matrix, which is actually the projection of A onto our orthonormal basis. So we just substitute that in for here, and we arrive at the core Krylov approximation, which is W of tau equals the exponential of tau A times V, which is approximately the same as beta times V sub m exponential of tau H sub m times the unit basis vector. So yeah, if anyone that is really into classical simulation of quantum systems is watching this, I'd love to hear why this isn't more widely talked about, or maybe it is. Please educate me further.